are going to explain hashing. Hashing. BST, AVL trees, big O of log n for insertion, deletions and searches. Hashing is a technique used for performing insertion, deletions and searches in constant average time. Finding min, finding max, printing the whole collection in sorted order in linear time are not supported. A hash table data structure consists of hash function h and array of size n. Let's look at some examples. First, we design a hash table for a dictionary storing items, where sin is a 10-digit positive integer. Second, our hash table uses an array of size n equals 10,000 and the hash function h of x equals x mod n. Third, we use chaining to handle collisions. Fourth, assuming integer keys, how do we map keys to hash table entries? Hash functions and hash tables. A hash function h maps keys of a given type to integers in a fixed interval 0 to n, 1. Example, h of x equals x mod n is a hash function for integer keys. The integer h of x is called the hash value of key x. The goal of a hash function is to uniformly disperse keys in the range 0 to n, 1. A hash table for a given key type consists of hash function h and array of size n. A collision occurs when two keys in the dictionary have the same hash value. Collision handling schemes. Chaining, colliding items are stored in a sequence. Open addressing, the colliding item is placed in a different cell of the table. Design issues. There are a few design issues with hashing. First, hash function like for integer keys compression functions and for strings. Second, collision handling like separate chaining and probing. Examples of probing are linear probing, quadratic probing and double hashing. Third, table size, which should be a prime number. Hash functions. Division. h2 of y equals y mod n. The size n of the hash table is usually chosen to be a prime number to minimize the number of collisions. The reason has to do with number theory and is beyond the scope of this course. Multiply, add, and divide. h2 of y equals I plus b mod n. A and b are non-negative integers such that a mod n does not equal to 0. Otherwise, every integer would map to the same value b. Collision handling. Collisions occur when different elements are mapped to the same cell. Separate chaining. Let each cell in the table point to a linked list of entries that map there. Separate chaining is simple, but requires additional memory outside the table. Separate chaining. Use chaining to set up lists of items with same index. The expected search/insertion/removal time is big O of n by n, provided that the indices are uniformly distributed. Capital N equals hash table size. Small n equals number of elements in the table. If n equals big O of n, the expected running time is big O of 1. Load factor, separate chaining. Define the load factor lambda equals small n by caps n. SAM n equals number of elements in the hash table. Capital N equals hash table size. To obtain best performance with separate chaining, ensure lambda less than equal to 1. As we add more elements to the hash table, lambda goes up, which implies rehashing. Collision handling. Few ways for collision handling are: first, separate chaining. Second, probing like linear probing, quadratic probing and double hashing. Linear probing. Linear probing handles collisions by placing the colliding item in the next available table cell. Each table cell inspected is referred to as a probe. Colliding items lumped together, future collisions will cause a longer sequence of probes. Example: h of x equals x mod 13. Insert keys 18, 41, 22, 44, 59, 32, 31, 73, in this order. Remove 44, 32, 73, 31. Here is an example of linear probing. Search with linear probing. Consider a hash table A that uses linear probing. Get K. We start at cell HK. We probe consecutive locations until one of the following occurs. An item with key K is found, or an empty cell is found, or n cells have been unsuccessfully probed. Removal and insertion with probing. Remove K. Call get K to get the element. Should we set the now empty cell to null? No. It would mess up the search procedure. See example on the next slide. Return the element. A cell has three states. Null, brand new, never used. Get X stops when a null cell is reached. In use, currently used. Available, previously used, now available but unused. Get X continues the search when encountering an available cell. Example of available cells, key has value -1. Example with remove K. Linear probing, removal and insertion. To handle insertions and deletions, we mark the deleted cells as available instead of null. Remove K. We search for a cell with key K. If such an item is found, we mark the cell as available and we return the element. Else, we return null. Put K. If table is not full, we start at cell HK. If this cell is occupied, we probe consecutive cells until a cell I is found that is either null or marked as available. We store item K, in cell I. Load factor. In linear probing, define the load factor lambda equals small n by capital N, where small n equals number of elements in the hash table and capital N equals hash table size. To obtain the best performance with linear probing, ensure that lambda. As we add more elements to the hash table, lambda goes up, which implies rehashing. Another way of handling collision is quadratic probing. Main idea of quadratic probing is spread out the search for an empty slot. Increment by I square instead of I high equals plus I2, percent table size H0 equals hash, percent table size H1 equals hash plus 1%. Table size H2 equals hash plus 4%, table size H3 equals hash plus 9%. Table size. Example of quadratic probing problem. With quadratic probing, you can see that this works pretty well for an empty table and gets worse as the table fills up. There's another problem here. If a bunch of elements hash to the same spot, they mess each other up. But, worse, if a bunch of elements hash to the same area of the table, they mess each other up. This phenomenon is called primary clustering. Load factor in quadratic probing theorem, if table size is prime and lambda. For greater lambda, might not with load factors near 1/2 the expected number of probes is empirically near optimal, no exact analysis known. Don't get clustering from similar keys. Still get clustering from identical keys. Double hash injects in another way for solving collision. Idea, spread out the search for an empty slot by using a second hash function. No primary or secondary clustering. High equals plus I hash 2, mod table size. For I equals 0, 1, 2. Good choice of hash 2 can guarantee does not get stuck as long as lambda. Integer keys hash 2 equals r, where r is a prime smaller than table size. Example of double hashing. You can see that this works pretty well for an empty table and gets worse as the table fills up. There's another problem here. If a bunch of elements hash to the same spot, they mess each other up. But, worse, if a bunch of elements hash to the same area of the table, they mess each other up. This phenomenon is called primary clustering. Load factor in double hashing. For any lambda search cost approach is optimal. Successful search 1 by lambda times log 1 by 1 μs lambda. Unsuccessful search, 1 by 1 minus lambda. No primary clustering and no secondary clustering. Still becomes costly as lambda nears 1. Thank you for watching.